to the computer. Okay, sorry about that. All right. So that was the definition of the inner product. We talked about this last week. And then what else we talked about? We looked at some of the properties. That would be theorem 7, properties of inner product space. The first one was a 0, scalar 0. That's the dot product of the 0 vector with any vector. It's commutative, of course, and because of the symmetry axiom. And that will give you the scalar 0. Okay, and then the second one, again, you can think of this now as distributive property of inner product. You can do inner product of u plus v dotted with w. You can do u dotted w plus v dotted w. And the scalar multiple, u dotted with cv, again, you can bring c outside. And if you want, you can distribute c onto u and then comma v. Remember, c does not distribute to both terms. And that one, again, is consequence of the homogeneity axiom of inner product spaces. And then we talked about length, distance, and angle between two vectors. Remember the norm of the length, norm or the length of the vector is the magnitude, double vertical lines, magnitude of vector u is the square root of the inner product of u with itself, because u dotted with u gives you u squared, right? It gives you magnitude of u, that is squared. You take square root of that, it just gives you the length. The distance between u and v, that would be the tip-to-tip distance between the two vectors, is simply the magnitude of u minus v. The angle between them given by what you're looking at. So again, we went through all of these last time, and I just want to do a quick recap because it's been a week. Now, when we talk about, by the way, like distance, when it comes to inner product spaces, the book has this interesting example. You see this figure 510. So he's trying to clarify, if you will, or just give more insight into what do we mean when we say distance between two functions, right? It's just something that we've never done. So here, he has an example. So in figure 510, you have two functions on the left, two functions on the right. Now, if you look at the distance between f and g, 1 over root 30. Okay, and he shows you up here how he found that distance. Again, this part B, that's what I'm saying. What do we mean distance between f and g? But you can kind of holistically look at this one. And if you compare the figure on the left to the figure on the right, clearly you see the figure on the right, the distance, the gap between the two functions is more than the gap between these two functions. So in that sense, we can compare, let's say, distances between two, let's say, sets of functions. So the distance between f of x equal x, g of x, x squared, the one on the left, the distance between these two is less than the distance between the two functions on the right. So this is really, we're trying to make kind of lemonade out of lemons, if you will, because it doesn't make sense to interpret the distance between two functions. So this is what we're trying to, our best, trying to, again, shed some light into what do we mean by distance between functions. All right. And then, of course, we have this theorem 5.8, which brought these, a couple of inequalities we talked last week was Cauchy-Schwarz inequality. And number 2 was triangle inequality. With Cauchy-Schwarz, the inner product, absolute value of inner product is less than or equal to the product of the magnitudes of the two vectors. The triangle inequality, the magnitude of the sum vector would be less than or equal to the sum of the magnitudes of each vector. And finally, the third one is the familiar Pythagorean, if you call it identity, here we call it theorem, that if you have u and v are orthogonal, if and only if the magnitude of u plus v squared. Remember, you can think of that as a hypotenuse, u plus v. Remember, u and v are two vectors. U plus v give you the resultant vector, right? So if you use a parallelogram, you have two sides, u plus v gives you the diagonal. And once you can translate one of those vectors to create a triangle, then you can see that you have a right triangle here, sort of, kind of. The magnitude of u plus v squared is equal to magnitude of u squared plus magnitude of v squared. So those are the things we had. And then let's see, we talked about the orthogonal projection of vector onto another one. And what else? And these are the formulas for orthogonal projection. We will be using this formula this evening when we talk about Gram-Schmidt orthonormalization. We have to do projections of one vector onto another. So we will go in more details into this orthogonal projection later on and see several examples of this. And let's see, I think that was it. So once again, any questions, ladies and gentlemen, about any of the homework problems that you may have tried, had trouble with, or something you simply want to see how it's done, anybody, please tell me. Unless you tell me, I assume you're okay. And I think we did maybe a couple of exercises. I don't recall which ones, but let's see. These exercises are pretty straightforward, at least the ones I've done. But should we try to do an exercise, by the way, from this section? Anyone? Should we, just as a warm-up, to kind of see how things work out in this section a little bit? Let's do that. Now let's try. We're in section, so I'm going to look at section 5.2, and let's take a look at exercise. For instance, how about something for distance between two functions? So let's take a look at, or we can do angle between two vectors also. Let's look at a couple of these. So I'm going to go to, unless you have a specific one again, folks, I'm going to go to exercise number, something from calculus here, numbers 39 to 42. Okay, so let's take a look at one of these. I'm going to get my paper ready here, and then I'll switch to my notepad. So first I'm going to write the problem down. So in exercise number 40, so this is section 5.2, number 40. In the exercise, it says use the functions f and g in C bracket -1, 1. Now, what that means is that you're looking at as f and g is in the set of all continuous functions, the C for continuity here, over the interval from -1 to 1. So that's what that is. Now, in part A, the question says find the inner product, right? If angle bracket means inner product. So we want to find the dot product, inner product of FG. In part B, we want to find the magnitude of function f. And remember, again, what do we mean by magnitude of a function? This is kind of abstract ideas. And in part C, magnitude of g. And finally, in part D, the distance between two functions, something again that we really is hard to interpret unless we graph both functions and kind of look at the space, the area between them, how large, how small they are. So I'm now writing, and I'll share with you my notepad in a moment. I'm just writing the details here. I'm at the integral The inner product is defined as product of f by g. Okay, and we are doing number 40. In number 40, the function f of x is negative x, and the function g of x is x squared minus x plus 2. Okay, so now let me switch to my notepad here so you can see my notepad. And there you go. So hopefully everybody can see this now. Okay. So again, if you note for the set of continuous function in the interval from -1 to 1, you're given a specific inner product. So this is the definition of the inner product, okay? Which is common sense. We think of inner product as dot product, so they're multiplying them. They're not adding f plus g, because we're thinking, again, the keyword is product here, so multiplication. So this one, again, we are doing inner product. I do reference these dot product just to recall that these formerly, the Euclidean ones are dot product. These are not Euclidean. So I should really just call them inner product, maybe. But again, hopefully everybody's follows some from time to time, I call them dot product to remind you that a dot product is inner product. But these are inner product. Okay, whatever they are, right? Let's do this. So for part A, we're given these functions. Let's do the first part. So I'm going to do in part A. Now this is part A. So we're doing f comma g angle bracket. It's going to be -1 to 1. So f of x is negative x. So that's going to be negative x times the quadratic x squared minus x plus 2 and dx. That's by definition of inner product that was given. Okay. Now, this one is basic. The integrand, I'm sure everyone in this course right now here, the one you're here, are capable of doing this. It's very simple integral, right? So what I'm going to do is I'm going to distribute x, negative x, to the quadratic and take the integral. So first one, negative x times x squared is negative x cubed. And then negative x cubed. So what do we do next with that one? Negative x cubed, the integral of negative x cubed is going to be negative x to the 4th over 4, right? The power rule of integrals. And then the next one, negative x makes positive x squared. The integral of x squared is 1/3 x cubed. Again, basic calc 1 type integration, nothing drastic. And then the integral of negative x times 2, that's negative 2x. That integral is going to be negative 2x squared over 2, or simply negative x squared, right? Evaluated from -1 to 1. And then the next step, of course, you can do the fundamental theorem, right? The fundamental theorem of calculus. Plug in the upper limit minus lower limit. So the upper limit, you put 1 in for x. So I'm going to get -1/4 plus 1/3 -1, right? That's when you plug in 1, the upper limit, minus, and then we plug in the lower limit. For the lower limit, we plug in -1 in for x. -1 to the 4th is 1, so that's again -1/4. -1 cubed is -1/3, so that's -1/3. And the last one, you square the -1, you get 1, and then negative on the outside. There you have it. And then we can combine them now. So if you notice, I have negative, for instance, negative of -1, that makes it +1. So these cancel. I have negative of -1/4. Negative of -1/4 is quarter, and -1/4. So these cancel. And then the answer is going to be 1/3. That's this first third. And then negative of -1/3 is 1/3. 1/3 and 1/3 makes 2/3. And there you go. So that would be the inner product of f and g. That is part A of this exercise. Is everyone okay with part A? Are there any questions in part A? No? Okay. We're good. So let's take a look at part B now. So in part B, we want to find the magnitude of f, right? The magnitude of the function. So the magnitude here for part B, well, we know the magnitude of any vector squared is the inner product of the vector with itself, right? So we're going to have to do the inner product of f with itself. What does that mean? This time, the second function, instead of g, we have f. So that means f comma f. Let me write that. So that means f comma f. I have to do -1 to 1 of the first function times second function, which happens to be f again, and then dx. And there you have that inner product. So all I got to do is just do integral -1 to 1 of f of x. F of x is negative x. So you just multiply negative x times negative x dx. That will be integral from -1 to 1 of x squared dx. Again, the integration for you folks anyway is trivial, right? You can do this while you're doing other tasks, the integration parts. So the integral of x squared, that would be 1/3 x cubed. True, 1/3 x cubed, evaluated from -1 to 1. You plug in the upper limit, you get 1 minus, plug in the lower limit, you get -1. So it's 1/3 of 1 minus -1, and the whole thing is, again, 2/3. So that's going to be, again, that's the magnitude squared, right? Therefore, the magnitude of the function is, we simply take the square root of this, right? It would be positive root of 2/3. And for what we do in this course, don't worry about rationalizing and all that. This is good enough. In part C, we want to find part C, magnitude of G. So we're going to do the same thing. That means to find magnitude of G, let's look at magnitude of G squared. Because we need to relate these to their inner product. That's why. Otherwise, I cannot find the magnitude. Because I'm not given like a vector, right? You square the first, square the second, square the third component, take the square root. It's nothing like that because we're just doing the inner product. Okay, G inner product with itself. This time, remember, G is the quadratic function, x squared minus x plus 2. That's going to be x squared minus x plus 2 squared because you're multiplying it by itself, right? Dx, and now I can expand this trinomial and -1 to 1. And one way you can expand this, you can write it as a quadratic times quadratic, FOIL, distribute, combine like terms, and all that stuff. So that's one way to do it. Another way to do this is the following. You square each of these, because that's squared. So I do x squared squared, x squared, 2 squared. So we're going to write those down. And then, you know, with the square of a binomial, you also do twice first by second. But we're going to do that. We're going to do twice first by second, twice first by third, and twice second by third. That would also work. So here's all said and done. This is what I'm saying, proposing. Square the first one, plus square the second one, plus square the last one. That's each of them squared. And then we go plus twice first by second. So it's going to be -2x cubed plus twice first by third. That's going to be twice x squared. And then plus twice second by third. Well, 2 times -x is -2x. And there you have it, dx. So that's how you can expand this. Now, once we combine like terms, let's see, what do we get? On the fourth, the only fourth degree is x to the fourth. So here's x to the fourth. And then the cube terms, I have only negative 2x cubed here. So that goes right next to x to the fourth. Right, now x squared. I have an x squared here. And 2x squared, so that makes it 3x squared. And there's another x squared here, right? 2 times 2. So for x squared, just to make sure we get it, so it's negative 4, 2, and 1. So what do we get? We're going to get, let's see, negative 4, negative 4. Make sure I got the signs right, please, everyone. So twice first by second, that's good. Twice first by third. Oh, wait a minute. Twice first by third, that's 4. Right? You guys didn't catch me. There you go. That's going to be 4. That's twice first by third. And then twice second by third. That looks good. Now it's better. Okay, 4x squared, negative 4x squared. So that's x, sorry. Yeah, 4x squared and x squared is 5x squared. Yeah, please verify. I think that looks right. So it's 5x squared. The x term, I have negative 4x. That's negative 4x. And the constant, the only constant is 4. That's plus 4 dx. And of course, the integral, again, is going to be trivial for all of you. It's going to be 1/5 x to the 5th power negative 2x4 over 4. So that's 1/2 x4. 5/3 x cubed negative x squared over 2 is 2x squared plus 4x negative 1 to 1. And then you go upper limit minus lower limit. The upper limit, remember, you're putting 1 in for x's. So we're just going to get the coefficients. And 5/3 minus 2 plus 4 minus, plug in the lower term, the lower value. Negative 1 to the 5th is negative 1. Negative 1 to the 4th is 1. Negative 1 cubed is negative. Negative 1 squared is positive. And negative 4 times negative 1 is negative 4. There you have it. Now let's see if we can cancel some things. These are all 5/3. Okay, negative 1/2 and positive 1/2. Those cancel. Positive 1/2. And then we have negative 2 here and then positive 2 here. Those cancel. So the fraction is going to be negative 1/5. That's positive 1/5. So I got 2/5. And 5/3 and 5/3, who makes 10/3. 4 and 4 makes 8. The LCD is 15. Right? So I multiply the top and bottom of the first fraction by 3. Top bottom of this fraction by 5. And top and bottom of 8 by 15. 8 times 15 is 120. So we get 176/15, unless I made an arithmetic error, but it looks pretty good. So that's magnitude squared, therefore magnitude of vector G, which is function G here. Remember, if we can think of them as vectors here, vector objects, and there you have it. So it's going to be squared root of that. Okay. And again, hopefully everybody's okay on the work we've done here. And then we're going to look at part D. In part D, we want the distance between the two functions f and g. So let's take a look at the distance between two functions. So this is 5(2), number 40, continue. Okay, in part D, the distance between f and g. The distance between two functions is going to be the magnitude of f minus g. Okay, so before we find the magnitude of f minus g, we need to find what f minus g of x is, right? F minus g of x is, and f minus g, that will be easy because we know what f is, we know what g is. So we're doing f minus g. We do negative x minus the quadratic. The x's add to 0, right? So f minus g is just going to be negative x squared minus 2 because we're doing negative of g. So I'm going to write that. So f minus g is going to be negative x squared minus 2. And then to find now the magnitude of that, we know the magnitude squared, right? Magnitude of f minus g squared is the inner product of f minus g with itself there. So that means this time f minus g, we're doing inner product of negative x squared minus 2 with negative x squared minus 2 with itself. And by definition of inner product that we had, that's the integral from negative 1 to 1 of the product of these two, negative x squared minus 2 squared, right? Dx. And of course, you expand the binomial here, and what are we going to get? We're going to get negative 1 to 1 of x to the fourth plus 4x squared plus 4 dx, right? You square the first, twice first by second, and second squared. And then you integrate these again, 1/5 x to the fifth, and plus 4x cubed over 3, 4/3 x cubed plus 4x, evaluated from negative 1 to 1. Okay, and then we do the fundamental theorem, upper minus lower limit. So the upper limit is going to be 1/5, 4/3 plus 4 minus the lower limit. The lower limit's going to be when you plug in the negative. Okay, so the lower limit is going to be negative 1 to the fifth is negative. That's negative 1/5. Negative 1 cubed is negative. So that's negative 4/3, and negative x makes this negative 4. 1/5, negative 1/5, that's 2/5. 4/3, negative 4/3, that's 8/3. And 4, negative 4 is 8. And combine these. Here's LCD. Top bottom of the first fraction by 3 makes that 6. Top bottom of the second fraction multiplied by 5 plus 40. Top bottom of 8 by 15, we get 120. Again, that's 166 over 15. But that's the magnitude squared. So the magnitude of f minus g, therefore, is just the square root of 166 over 15. And there you have that one. So there, it's just an exercise in this section. Hopefully everybody's okay on this one. Any questions, ladies and gentlemen, again, on this example we did? And in the rest of it, I think you're going to be fine. If good, because it's 6:52, let's actually go ahead and get started. So we're going to finish this section 5.3. Let me go back to my, you still should be able to view my notepad. Okay. Again, if everybody's good, let's continue on with what we're about to do here. So in section 5.3 now, this would be again the last section formally for us. Section 5.3, let's talk about the Gram-Schmidt process here. Okay. So, uh, interesting, again, process. What do we want to do in this section, right? So our objective, I've written what our objective is in this section. What we want to do is we would like to be able to uh, find bases that are mutually orthogonal and they have a unit length. So in other words, the vectors in the basis each will have a magnitude of 1. That's all that is. Okay. Now, real quick about the name Gram and Schmidt here. Gram and Schmidt were two mathematicians. Gram, I believe, if I recall correctly, Gram was a Danish mathematician. And actually, in his dissertation, the contribution to this, what we're about to study, were formulated. So that was Graham's doctoral dissertation, actually. Now, his work primarily was in abstract algebra, and he was the gold medal recipient from the Royal Danish Society, I believe. So that's a little background on Graham. Now, Schmidt, the other mathematician, last name sounds German, and it is his first name was Erhard Schmidt. Now, we're talking about late 19th century, early 20th century. Okay. In fact, this Gram-Schmidt, the publication of this theorem, this work was in early 1900. Now, Schmidt actually, he was the mathematician who worked under Hilbert. Some of you may have heard the name Hilbert, but Hilbert is a big name in the field of abstract algebra. And he's the one that actually came up with the general concept of Hilbert spaces named after himself. And those Hilbert spaces are simply the study of infinite dimensional vector spaces. Very fascinating stuff. So that's just to give you some motivation into what we're doing here as far as the background of these mathematicians go. So again, our objective, very simple. We want to have bases, because remember the advantage of a basis, if we have bases, we can write every vector in the vector space using these bases vectors. Well, wouldn't that be nice if these vectors were orthogonal and unit vectors? Okay. Now, the orthogonal that we talk about here are mutually orthogonal. And here I have the definition for you. So what do we mean by orthogonal and orthonormal sets? Okay. First, orthogonality. Now, when we say orthogonal, by the way, think perpendicular. Orthogonal, perpendicular. So if two vectors are orthogonal means one vector is perpendicular to the other. That means the angle between them is 90 degrees. Okay. So a set S of vectors in an inner product spaces. I'm just reading this definition now. It's called orthogonal when every pair of vectors in S is orthogonal. Every pair. So what do we mean by every pair? So for that one first, let's say I have a set. Okay, I'm going to put this as a note for you. So note, let's say my set S in here is a set that's made up of a bunch of vectors. So I have V1, V2, however many vectors are in the vector space. So let's say in R3, chances are there are 3 vectors. In R2 would be 2 vectors. In Rn would be Vn. Okay. So the first part, the orthogonal when every pair of vectors is orthogonal, that means this. If you look at Vi, Vj, those are 2 vectors in this set. They're orthogonal. That means their inner product And again, indirectly, think about the dot product. The dot product, inner product of those two must be scalar 0. Okay, and that's for whenever I is different from j. It means two different vectors. That's all I different from j means. So remember here, I and j both go from 1 to n. So for example, v1, v2, I is 1, j is 2. So that's what we mean. If I is equal to I, so v1, v1, that's the inner product of a vector with itself, right? That gives you the magnitude of the vector squared. So we don't want that. We want the dot product, the inner product, to be 0. That makes them orthogonal. Now, in addition to being orthogonal, if each vector in the set is unit vector, that means it's a vector of length 1, magnitude 1, then this set, it's called an orthonormal. Ortho, the first part of the word orthogonal, and then the normality, orthonormal, because you normalize the vector, turn it into a vector of magnitude 1. So that's why it's called orthonormal, orthogonal and normalized. So for this part, the orthonormal part, the normal part of that, the magnitude of any one of these vectors has to be 1. So if these two conditions hold, then we have what we call an orthonormal basis for the vector space. Okay, and that's what that is. Now, and again, please, if you have any questions, feel free to ask, folks. Now, let me put another note in regard to this, by the way. So what if this set S is a basis if set S is a basis? Because the definition doesn't require it to be. It just says, suppose you have a bunch of vectors. There you go. As long as this holds, then this is an orthonormal set. Now, if the vectors in this set are basis vectors, then we say that this is an orthonormal basis. Orthonormal basis. That means every vector in this set, again, is mutually perpendicular, orthogonal, and every one of those have magnitude 1. Now, you already are probably familiar with some orthonormal bases, right? So there are many, in fact, non-standard orthonormal bases in Rn. There's many of them. And there is, for instance, if I look at the standard basis, standard means Euclidean. The standard basis in R2. Okay, if I look at that. What are the standard bases in R2? Vector 1, 0, and 0, 1. There you go. So here's like my V1, here's V2 in reference to what's up here. See, I have a set, and this is what set S is. There you go. These are the basis vectors. It means every other vector in R2 can be written as a linear combination of these two. Okay. Now, if you look at the dot product, let's look at the inner product of 1, 0 with 0, 1. Because this is a standard basis, the inner product turns into a dot product. Remember, dot product, you multiply first component by first plus second component by second. 1 by 0 plus 0 by 1, you get a 0. So the dot product is 0. That means they are orthogonal. If the dot product is 0, they're orthogonal. That means the angle between them is 90 degrees. Now, what's the magnitude of each of these vectors? The magnitude of V1 is the square root of 1 squared plus 0 squared, which is 1. See, it's a unit vector. What's the magnitude of V2? That's square root of the 0 squared plus 1 squared. Again, it's 1. So both of these are have magnitude 1. Therefore, the set S is an orthonormal set. Orthonormal basis, because its vectors are basis vectors. Basis for r squared. Now these vectors, again, I'm sure you've seen them in other form also, like this. Remember, the first one is the I vector. This one, the I vector is 1, 0. The second one is the j vector, 0, 1. So the ij in 2-dimension, and you've seen the graph of these, right? There you go, ij, the two vectors, and the angle between them is 90 degrees. You've seen probably the 3-dimensional version of this one with ijk. So this is an orthonormal basis. Now, I mentioned there are many non-standard other than these bases in Rn. Now, let's take a look at another example here. So this time I'm making a non-standard basis. 1, 1, and let's make this other one 1, 0. All right, and then let's do the dot product again. So I have call this W1 to be different than the one above, W2. The dot product, W1, W2. The inner product in this case is going to be the dot product, or we can stay with the inner product. So this is going to be 1, 1. Right, the inner product is going to be 1 times 1 plus 1 times 0. So that's going to be 1. Right. So this is again non-standard, right? So let's see what's the magnitude of these. The magnitude of W1 is the square root of 1 squared plus 1 squared, which is square root of 2. So notice these two are neither orthogonal nor magnitude is 1. So this is non-standard basis in R2. But the standard one is orthonormal. This is not an orthonormal set. It is a basis, but it's not an orthonormal set. Okay. Okay. So again, the fact that the dot product is that means this is not orthogonal. And the fact that the magnitude of one of them is 2, even if the other one was 1, which it is, this one is magnitude 1. But this is not normal. Normal in a sense that it doesn't have a magnitude 1. So it's not an orthonormal set. Okay. So hopefully, again, everybody's okay on this work. Now, if no question, let's take a look at another example here. Okay, so for this next example, let's say that we are in P3. That means we're looking at all third-degree polynomials with standard inner product. Remember, the standard is the Euclidean one, it's the dot product. Okay. And here's what we mean. When I do the inner product of two third-degree polynomials, we multiply the constant together, the coefficient on the x terms together, the coefficient on the x squared terms together, and the coefficient on x cubed terms together. In this light, p of x is a0 plus a1x, a2x squared plus a3x cubed. So that's what px is. And of course, q of x would be written similarly. That's going to be the constant, coefficient on the x, coefficient on the x squared, and the coefficient on the x cubed term. So those are the two polynomials. Okay. So this inner product, suppose this is the standard basis. It is our standard basis here. Okay. Now, the question we want to ask is this. Let's say I want to know if the basis, this set S is now B. This set B, which is made up of 4 vectors, V1, V2, V3, V4, and is going to be equal to, let's say we're going to go 1x, x squared, and x cubed. If this set, the basis, is this orthonormal, there you go. That means all the inner products, in this case, would be the dot product because these are Euclidean. Is the dot product pairwise dot products? Every one of those must be 0. And the length of each of these vectors has to be 1. So here we go. First, for the answer to orthogonality. So let's check orthogonal first. Okay, so to be orthogonal, for instance, I'm going to look at the inner product of V1, V2. So what does that mean? Well, V1, remember, is 1. That's our first vector. It's going to be 1. Inner product with X. Okay, so what does this vector V1 look like as a vector? So vector V1 is going to be 1, right? It's just 1. That means x, x squared, x cubed will be each 0. So those other components are 0. So this is what it looks like as a vector. What does V2 look like? V2, again, it only has x. The other components are 0. So 0, 1, 0, 0. V3 is going to be 0, 0. Only the coefficient on x squared is 1. And for V4, we go 0, 0, 0, and 1. That will be the coefficient on x cubed. Now, so I'm doing the inner product of 1 and x, means this vector 1 and x would be vector 2, right? Let's do that dot product. That would be 1, 0, 0, 0, dotted with 0, 1, 0, 0. And remember, for dot product, standard dot product, you go first by first, second by second, third, third, fourth, fourth. So we go 1 by 0 is 0, plus 0 times 1 is 0, plus 0 by 0, 0 by 0. Those are zeros. So there you go. That dot product is 0. If I look at V1 and V3, let's do that dot product. Again, V1, that means I have to do 1 comma, V3 is x squared. So I'm doing the inner product of 1 and x squared, those two vectors. That means I'll be doing 1, 0, 0, 0, dotted with the V3, which is 0, 0, 0, 0, 1, 0. And this dot product, you can see it's 0. Well, how many combinations are there, by the way, here? Because we have 4 vectors. We're looking at mutual pairs. So it turns out to be a problem in combinatorics as far as how many there are. So you probably have seen this notation. The 4 choose 2 notation gives you the subset of size 2 from a group of size 4. That's what I'm doing here. So that's going to be 4 factorial, 2 factorial, 4 minus 2 factorial. This is, you've known this, you've seen this as the binomial coefficient. Remember this one, folks? You must have seen this either in the expansion of the binomial expression or in your second semester calculus. These were the coefficient for the binomial series. So here's n factorial, x factorial, n minus x factorial. That was the general form that I'm doing up here. This expression, 4 factorial, is 4, 3, 2, 1. So that's, what would it be? That's 24. That's 4, 3, 2, 1. 2 factorial is 2. And 4 minus 2 is 2 factorial is 2. 2 by 2, 4. 24 by 4 is 6. There you go. There are 6 pairwise comparisons here of these 4 vectors. So we've done 2 of them. You can show the other ones. Let me do one more. And V4. We really have to show all 6 of these folks. I've shown 2. This is the 3rd one. Feel free on your own to show the other ones that work. V3, 4, that means the inner product of x2, x squared, x cubed, those objects. And that inner product's going to be, remember, for x squared, that's 0, 0, 1, 0. Dot it with x cubed, which is 0, 0, 0, 1. And again, by definition of dot product, 0, 0, 0, 0, 1, 0, 0, 1. All of those products would be 0. We just put 0 there. And therefore, we go, therefore, again, I skipped 3 of those. You can try them. Therefore, these are mutually orthogonal. Okay, so that's what those are. Everyone okay on this work? No questions? If no questions, then let's now check out their magnitude. We want to see if they are now normal. So let's check out the magnitudes of each of those vectors. So we're looking at the magnitude of each vector. The magnitude of vector 1, that's the magnitude of this vector. And you can see here, I'm just going to make this go a little faster because every one of these vectors has only 1 for the components. So the magnitude is when you square each of these, add them up, take the square root. Let me do magnitude of 1, if you will. There you go. Do inner product of 1 with itself. That's magnitude of 1, right? That's going to be square root of 1, 0, 0, 0 dotted with itself, 1, 0, 0, 0. And that magnitude, that's the dot product is 1, square root of that is going to be 1. And likewise, you can show magnitude of x again. It's the same thing because you're doing, let me write it in the form that you become more familiar with. There you go. This is going to be 1 also. Magnitude of x squared, that would be square root of the inner product of x squared with itself. That's going to be 1. And finally, magnitude of x cubed is square root of the inner product of x cubed with itself. And that's going to be 1. So every one of these mutually orthogonal, and now every one is a unit. These are unit vectors. All right, every one is a unit vector. Therefore, this is an orthogonal set. So therefore, the set is orthogonal. Therefore, B is an orthonormal set. Mutually orthogonal, and the magnitude of every one of them is 1. Okay. And there you have this one. Now, hopefully everybody's following this. And for the next part, so I don't have to write these, let me now change my share. And again, hopefully everybody's okay. I don't see any questions in the chat. So again, please ask folks if you have any questions. Let's go back to the page of the book now. We're going to make this go a little faster. Okay. We are at theorem Theorem 510. This is where we are. Okay, now Theorem 510 tells us that the orthogonal sets are linearly independent. Okay, so now here's how the theorem goes. The proof's there if you want to look at the proof. But suppose we have a set of vectors. This is now a set whose vectors are mutually orthogonal, and each of those v's have magnitude 1. So suppose we have an orthonormal set, okay, in this inner product space V, then if that's the case, then set S is linearly independent. So when we say linearly independent, that means if you look at the linear combination of them right here, remember this was like on your exam also. We can show that the linear combination of those will equal to 0. The solution to the homogeneous system has only trivial solutions, right? That means all the C's must be 1, otherwise it's not linearly independent. There you have it. Now, the converse of this theorem, by the way, folks, is not true. The converse of this is not true. So what we mean by that is this. If a set S, the vectors are linearly independent, they need not be orthonormal, right? Well, actually, this is orthogonal. So sorry, this is orthogonal, not orthonormal. This is, again, I said orthonormal earlier. Sorry about that. It's orthogonal. So if we just have linear independence between vectors like the ones on the exams, many of those were not orthogonal. So the converse of this isn't true. Okay. So let's see. Now, theorem 10, a corollary to the theorem goes like this. If the vector V is inner product space with dimension n, then any orthogonal set is a basis, forms a basis. Remember, because they're going to be linearly independent, right? And they are mutually perpendicular. So they're going to form a basis. And that is a corollary of this one. Okay. And let's see. So again, orthogonal implies linear independence, and that implies that this is a basis. Now, the fact that it forms a basis, that comes from the theorem in chapter 4, actually. In chapter 4, we had a theorem that said for linearly independent set, they're a basis. Remember, even on the exam, you had to do that. You had to show that this set was basis. All you did was shown that those vectors were linearly independent. And you showed that by looking at the Gauss-Jordan. You said the vectors, once you do the solution to homogeneous system, you only get trivial solutions. So there you have that one. Okay, and again, hopefully everybody's good on this work. Now, let's see. Let's take a look at, just to clarify this, let's take a look at an exercise here. So I'm going to go to, and then we'll come back to this. We still haven't talked about Gram-Schmidt, right? That's coming up, very close. But I just want to do an example of what we've just talked about. So let's take a look at exercise. We're going to look at exercise number 10 in here. Okay. So first, in this segment of the exercises, part A, the question reads, determine whether the set, I'm going to write this in my notepad, section 5.3, exercise number 10. So in part A, determine whether the set of vectors is orthogonal. Part A is, I'm just going to say orthogonal. And for number 10, by the way, let me write the vectors. So this is in R3, we have root 2 over 2, 0, negative root 2 over root 2 over 3, sorry, not 2. Root 2 over 3, 0, negative root 2 over 6. The second vector is 0, 2 root 5 over 5, and negative root 5 over 5. And the last vector in number 10 is root 5 over 5, comma 0, comma a half. Okay. So again, we are given 3 vectors in number 10. Part A, are they orthogonal? In part B, if the set is orthogonal, if orthogonal, then determine whether it's orthonormal. Does that imply that is orthonormal? Remember, orthonormal is the orthogonal set where each vector is magnitude 1, right, in the set. And in part C, determine whether the set is a basis. Is the set called the set, S in generic form, is S a basis for, in this case, R3, because we have 3 vectors, so this is R3. Now, let me switch my share to my notepad. Okay, so I have written this for you now. First, orthogonality. To show this orthogonal, part A, are these vectors orthogonal? And these vectors, by the way, here's V1, V2, V3. So we have 3 vectors in that set. Remember, we have to show, well, you tell me, anyone want to jump in? Feel free to do. What do I need to show in part A to show that these are orthogonal? Anyone? To show that the vectors are orthogonal. Anybody want to take a shot at that one?
Prove that they're 90 degrees.
Good. 90 degrees, the angle between them. And how do we show that? That the angle between them is 90, other than showing the cosine of pi over 2. We don't want to use theta to show that they are orthogonal. What should their dot product be? The dot product should be 0, right? The dot product has to be 0. So let's do the dot product. Because if the dot product is 0, then the numerator of the formula for cosine theta is 0, right? If the dot product is 0. And the only time cosine theta is 0 between 0 and pi is when theta is pi over 2. Theta is angle between the 2 vectors. Pi over 2 means 90 degrees. Okay, so let's do the dot product. And without writing this, let's say V1 dot V2. You multiply the first components, second component, third components. First by first gives you 0, right? So the dot product will be 0 plus. Second by second would be 0 plus. The third component of the first vector, it's negative root 2 over 6 times the third of the second vector. Whatever that is, it is not 0. So that's it. The set is not orthogonal. It is not orthogonal set. Even if, say, V1, V3, V2, V3 are, they have to be mutually orthogonal, means every pair has to be orthogonal, mutual with respect to one another. Now, in part B, it says if orthogonal, are they orthonormal? Well, they're not orthogonal, so we can't say they're orthonormal, right? Therefore, that's pretty much given. In part B, the result of this results that they are not. The part that it fails is the ortho part. orthonormal, even if the magnitude is 1. But we can actually see even the magnitude won't work. Look at magnitude of V1, for example, this vector. Remember, to do magnitude of that, you square the first component. We get 2/9 plus second component is 0. Squared is 0. And the third one is negative root 2 squared, which is going to be 2/36. And my pen just ran out of ink, so I'm just going to use another pen. Sorry about that. Been writing a lot lately, so I'm using up a lot of ink. Okay, so that's the magnitude of this vector, square rooted. And you can see clearly this square of that is not 1. There you go. Okay, when you combine those two fractions, you don't get 1. So they're not orthonormal. They're not only not orthogonal, they're not even magnitude 1. Now in part C, is this a basis? Now, it still could be a basis, couldn't it? We just want to see if we have an orthonormal basis. So all our bases that we worked up until today, they did not have to be orthonormal, and they were basis. Like on the exam, we had basis. They were not orthonormal. So let's see if S is basis. So to see if S is basis, that means these vectors do not lie on the same plane. Then we need to look at the solution to the homogeneous system, right? So we have root 2 over 3, right? 0, negative root 2 over 6. That's my first vector. The second vector is 0, 2 root 5 over 5, and a negative root 5 over 5. And the third vector is root 5 over 5, 0, and 1/2. There you go. So I set up a system. And again, I'm thinking this. We're thinking the linear combination of C1, V1, C2, V2 plus C3, V3 equals 0. That's what I'm doing right now. I'm looking at that linear combination. Now for this one, if you go and actually do Gauss-Jordan on this, do GJ, Gauss-Jordan, I've done. And the Gauss-Jordan on this, I used Symbol Lab, to be honest, did not do it by hand. So I got 1, 0, 0, got the identity matrix, which indicates that the system has trivial solution. Remember, this means like x1 is 0, x2 0, x3 0. There you go. And in this case, of course, it means all the C's are zeros. This implies C1 equals C2 equals C3 equals 0. That means there's only trivial solution, right? The matrix has only trivial solutions, and therefore, by theorem in chapter 4, the set is, the vectors are independent. So the set is an independent set. So what's the answer to the question? Is S a basis? Remember, we had that theorem in chapter 4. If they're independent, then S is a basis. So we're just going to say yes, S is a basis for R3. There you go. It forms a basis. It's not an orthonormal basis, right? But nonetheless, it is a basis. Okay, so hopefully, again, everybody is okay on this work. Now, having done this, I think we are in a position to talk about the projections, and let's see. Yeah, let me go back to the book. I'm going to change my share to the book, page of the book, right here. So let me go back up here now. And we talked about this theorem, and hopefully now this theorem makes sense, and theorem 10 as well. Let's take a look at now theorem 11. Okay. Theorem 511. Let me see something here. Actually, before we look at theorem 511, let me kind of show you the motivation for that theorem. So I'm going to actually go back to my notepad. Okay. We're going to do something different. And then we'll relate this, what I'm about to show you, to that theorem 11. All right. So here we are. For this, again, this is the motivation for the theorem before we are about to see. So, in fact, I'm just going to call it that. Motivation for theorem 511. Okay, so for this one, suppose I have a basis, okay, that's made up of two vectors. So I'm thinking R2. So we have our basis has two vectors, and I'm going to stay with standard bases that are orthonormal. So I and J form an orthonormal basis. And why? Because here's vector I, and here's vector J. You can see the dot product is 0. Magnitude of each of those is 0, is 1, is 1. Okay, so let me do a drawing for you. This one, let's say I'm drawing a vector W here. This is vector W, and I'm going to project it onto the x-axis so that this would be W1, and here, this is W1, that vector. The horizontal component or projection of that vector is W1, and the vertical projection, we're going to call that W2. Okay, so there we have those. Now, where are the ij vectors here? The ij vector, I is the horizontal vector of magnitude 1. So let's say this is I, and this is j. And as you can see, the reason we like orthonormal bases is because we can write any vector. Remember, we can project any vector into horizontal vertical components. And the horizontal vertical components, these will be scalar multiple of I and j, right? So that would be very useful in the work that engineers do. For example, you can break down the components of the vector into its coordinates relative to an orthonormal basis. Now, so what's going on with this, what I'm doing? First, my W. W is it's in an inner product vector space. Okay. My W is in R2. That means a two-dimensional vector. So if you look at vector W, we can break it into two components, W1 and W2, right? A horizontal vertical component, and the W is going to be the sum of these two vectors. Okay, now W1 is simply the projection of W onto the I vector. So I'm going to write that. This is from last week, folks. Projection of W onto the I vector. And W2 is simply the projection of W onto the J vector, right? Onto J vector is W. Now, last week in section 5.2, let me recall what we talked about in section, because we're going to need what we're about to write here. In section 5.2, this is from last week, folks. When we talked about the projection of a vector onto another vector, We said projection of U onto V is given by the dot product of UV over the magnitude of V squared times vector V. This is from last week. Now, in here, because we're projecting onto the ij, those unit vectors, so I'm going to let V is what's being projected onto. I'm going to let V be I, for example. I'm looking at W1 and I. We're looking at this one. Okay. So the projection, therefore, of U, the vector onto I, is going to be U dot I. The numerator is going to be U dotted with I over the magnitude of I vector squared times I, right? Now, magnitude of I, because it's a unit vector, I and j unit vectors, each of those have magnitude 1. So the denominator is 1, therefore the numerator is just U dotted with I times I, which gives you a vector in the direction of I. That's W1. See, it's in the direction of I. W2, a vector in the direction W2, a vector in the direction of J. So now, from this, what we just showed, I'm going to replace these projections with what I just wrote down. So this is what we're doing. I'm doing, because it's dot product, see here, U dot I, that's the Euclidean product. I'm going to write it in inner product notation, right? So if I do inner product of W with V1 times V1 plus inner product of W with V2. Remember, V2 is the J vector, with V2 in the direction of V2. For this, what I'm doing right now, for this specific example, the first part, the inner product is going to be that. It's going to be, except instead of U, because that was section 5.2, I'm going to use W, because we're projecting W, not U. That's just a derivation I use U for. So we're going to go W dotted with I in the direction of I. And for inner product of WV2, we're going to go W dotted with J in the direction of J. Now, remember the Euclidean dot product, scalar product. It's just that when you do dot product of W dot I, we get a constant. I'm going to call that C1I plus this dot product is going to give you C2J. Okay, so what does that mean? We were able to write W as a linear combination of first and the second vectors. There you go, in the basis. So any vector W could be written as a linear combination of the ij vectors. So what this implies, therefore, is that we can say W in this case is a linear combination, right? So I'm going to write that. W is a linear combination of basis vectors. And there we have that one. Okay. Now, the coordinate representation, we can write as such. W using the basis vector as a coordinate is going to be that. This is called the coordinate representation. Okay. So to give you a quick, easy example, let's say my vector W is 3, 5. In this drawing, X is 3, Y 5. Okay. According to what we just derived, I can write it as C1. Here's my C1, and here's my C2. I can write it as C1I plus C2J, these projections. That means I can write it as 3I plus 5J. And this is what we call the coordinates relative to an orthonormal basis. These are the coordinates, the 3, 5, relative to ij. ij were orthonormal bases. Okay. So this is now, hopefully everyone is able to follow this. And now we can look at the theorem. But before we actually look at this theorem, folks, I'm looking at the time here and it's 7:43. I don't want to go too long without giving you a break. So if it's okay with everyone, let's take our usual break here. And sorry, I went a little bit over. So we will come back and go over that theorem and we'll look at the Gram-Schmidt when we return. So let's take our usual break. Let me pause this first of all, the recording. All right, so again, before the break, we just looked at this example, which I called motivation to theorem 511. So let's actually now go to that theorem 511 here. So I'm going to go to the page of the book. All right, so here's 511, and hopefully now this theorem makes sense. The theorem is titled Coordinates Relative to an Orthonormal Basis. So suppose we have a basis B that's made up of vectors V1 through Vn, and this time we want B to be orthonormal. So remember, that's the IJK kind of set. It is an orthonormal basis for an inner product space of V. Then the coordinate representation of any vector W relative to B is given by this formula. And that's exactly what I had in my notes that I did as a motivation. So you do inner product of WV1 times V1. Remember the first part here, that inner product, you can think of it as a dot product. So this part would be a dot product of W dotted with V1, which will give you a scalar multiplied by V1. So you have a scalar multiple of V1. And if you only have V1, V2 in R2, then this is like in the X direction. And this one would be in the Y direction. If you have V1, V2, V3, this would be in the X direction, the component of vector W in the J direction, and the third one would be in the K direction. And hypothetically, you can go to nth dimension, what we're doing here. Okay. Now, having done that, let's talk about Gram-Schmidt orthonormalization. So, for Gram-Schmidt orthonormalization, let me see. We can just go right to this one. So the question that Gram-Schmidt is trying to address is this. Well, how do we find orthonormal basis? There you go. Because that's what we like working with, right? If I can write every vector as a linear combination of basis vectors, then bases that are orthogonal, again, the IJK would be a reference. How do I actually come up with those orthogonal orthonormal bases? So the process is a three-step process. You can see numbers 1, 2, 3. The first step starts with a basis for the inner product space. There you go. You start with a basis for inner product space. So you start with a set of vectors, in other words. Okay, it has to be a basis, right? So they must be linearly independent, and that implies this is a basis. Now, number two, once you have the basis, and again, mentally, I would think IJK. When I look at V1, V2, V3, I'm thinking IJK in my mind, trying to comprehend these. So you start with IJK kind of model. Number two, we need to convert this basis B, the set with these vectors, to an orthogonal basis. So first part is to turn them into orthogonal, and there you go. How do you do that? That's step 2. And this shows how. We'll do an example in a moment. We turn it into an orthogonal set, and then we need to normalize them, means make every one of the vectors in this set, these, remember, now W1 through Wn. This is the orthogonal set. Where do these W's come from? There you go. These are really projections. W1, projection of vector W, right, onto B1. Projection W2 is the second projection component, V2, and so on. These are all projections. And these B primes will be orthogonal now. Now, if you normalize them, means you divide each of these W's by their magnitude, W2 by its magnitude, Wn by its magnitude. That's what number 3 is. If you do that, then we normalize them. So the set B double prime now, it's made up of U1, U2, dot, dot, dot. These are orthonormal. The set is an orthonormal basis. Every vector in B double prime is going to be mutually orthogonal. That's from step 2. And they will have magnitude of 1 by process number 3. Divide a vector by its magnitude, it will normalize it. Sounds simple, hopefully doable. And he has kind of an image here for an R2 version of this. So here's vector W. This is V1, this is V2. The projection of V2 onto V1. This is V2, V1 is in this direction. That would be W1. The projection of this vector to over here, if this would be W2. W2 here, W2, it goes from projection of V2 onto V1 to V2. So W2 is V2 minus projection of V1, V2. And you see that right in here. So that will justify it from the graph. And there, oh, he has it here. It was right down here. Okay. So let's see how we're going to apply this, right? Let's see how we're going to actually do this work. So let's go to the exercises now. Skip these examples because that's all there is in this section. So I'm going to take a look at one where we actually have to, let me see, we did number 10. See what else, if there's anything worthwhile in here. This is normalizing. We'll do that anyway when we do Gram-Schmidt. Let's see, finding the coordinates, a coordinate matrix. Maybe number 22, we can do that one. Okay. Let's see, okay. Let's take a look at, let's see if there's any better one than that one. How about number 26? I'm thinking number 22 was fine. It's just all these radicals and stuff. Let's take a look at number 26. Okay, so in number 26, again, the question reads, find the coordinate matrix of X relative to the orthonormal basis B. Coordinate relative to orthonormal. Okay. So this is section 5.3, number 26. Let's take a look at that one. I'm going to write the matrix X, or you can think of it as a vector. The vector X is going to be 2, -1, 4, 3. The basis B, it's going to be, it has 4 vectors. So it's going to be 5/13, 0, 12/13, 0. and 0, 1, 0, 0, negative 12 thirteenths, 0, 5 thirteenths, 0, and finally 0, 0, 0, 1. Okay, so I copied the problem and let me switch to my notepad. There you go. And let's see, change the lighting here if I can. Good. So it's a little brighter. Okay, so for number 26, again, we were given the basis, and we want to find the coordinates relative to the basis. Okay, so what I need to do is I need to do this. I need to determine W, the inner product of W and V1. Okay, so this is going to be the dot product. W is the vector X actually here. There you go. X as a W here, your vector X in that theorem. So it's going to be WV1, and that means I have to do dot product of 2, negative 1, 4, 3, dotted with the first vector, basis vector in set B. So that would be 5 thirteenths, 0, 12 thirteenths, comma 0. Right? And the dot product is the standard Euclidean dot product. So we go 2 times 5 thirteenths, negative 1 by 0, 4 by 12 thirteenths, 3 times 0. 2 by 5 thirteenths, that's 10 thirteenths, plus, that's 2 by 5. And then plus 4 times 12, that's 48 thirteenths. Together they add to 58 thirteenths. And there we have that one. Okay, that's not the complete answer. Now we need to do W V2, right? The inner product of WV2, so that will be that dot product, 2, negative 1, 4, 3, dotted with the second vector, which is 0, 1, 0, 0. This would be easy because they're all 0 in the second vector. Just do the second component by second. That gives you negative 1. WV3, the inner product of W with vector V3, that's going to be just the dot product of that, right? 2, negative 1, 4, 3, dotted with 0, 0, 0, 1. And that's going to be what? That's going to be just 3, isn't it? Because these are all 0. 3 times 1 is 3. The others are 0. And let's see. So we got that one. That's, oh, I did W. Sorry, I did V4 because that was the easier one. I did it with V4. Remember, the vectors in basis are your V's, V1, V2, V3, V4. Let me actually do WV3. So that's going to be the dot product 2, negative 1, 4, 3, dotted with this one now. This one, the V3, dotted with negative 12 thirteenths, 0, 5 thirteenths, 0. I'm going to only multiply the non-zero elements of this one. That's first component by first is negative 24 thirteenths, 2 times that. And 4 times 5 thirteenths, that's going to be 20 thirteenths, negative 4 13. That's what that's going to be. So W relative to B. Okay, W relative to the basis vector is going to be, it's going to be 58 thirteenths, the first one. That's going to be 58 thirteenths, and then negative 1, 3, and negative 4 thirteenths. This is like writing your vectors using IJ, writing it in IJK component form relative to the basis. So these are the coordinates of, again, this vector, the coordinates of 2, negative 1, 4, 3 relative to the basis. These will be the coordinates. And of course, I'm going to transpose this to get a column vector out of that.
Can I ask a quick question by any chance?
Yes, please go ahead.
Does it matter the order? Because would the three be last, or does that matter because it's
Oh,
V4 and V3?
absolutely. Thank you. Thank you. Thank you for catching that, Megan, because I wrote it out of order here. Thank you. In fact, let me correct it. Thank you for that. Absolutely. Order matters. Thank you, Megan. Okay, so so V3, that's -4/13. Thank you, because it's relative to the basis. So yes, order matters, and this is going to be -4/13. And now this is the fourth one, 3. Thank you again, Megan. Yeah, absolutely. There you have it. Okay, now it looks good. We're okay. Again, thank you for that, Megan. I appreciate it. Everyone okay on this, everybody? We're cool. Awesome. Now let me go back, change it to let's actually do a Gram-Schmidt here. So let me change my share. Wish I could find a really easy, quick way to jump between these two. Okay, so there you go. So we did number 26. Hopefully everybody's okay with that. Again, all we did right now, it's like this, something you're familiar with. W was a vector in, let's say, R2, and we wrote it as components in the IJK form. That's all that is in terms of the components of the basis vector. In the example I had as motivation, reference that, and hopefully that will help us out. Now, let's do one of these, number 20, like 7 through 36. How about something, the numbers aren't so bad. Number 32, I guess, or 34, either of those. If you see one you want us to work together, by all means, call it. Should we do, I don't know, number 34, if that's okay with everyone? Let's take a look at number 34. So in number 34, I'm writing the information first. So the set B, which is made up of basis vectors in R3, it's 0, 1, 2, first vector. Then it's 2, 0, 0. Then it is 1, 1, 1. Okay. Now the question, apply the Gram-Schmidt orthonormalization process to transform the given basis. This is a basis in R3. This is in R3. To transform it into an orthonormal basis. So in other words, right now, the way it looks, if you look at the dot product of linear combination of these vectors, I'm sorry, not linear combination, just mutual. If you look at the mutual dot products, so V1, V2, V2, V3, V1, V3, like that, those dot products, they may be 0. Yeah, V1, V2, I can see is 0, right? You dot product the first from these two, that dot product is 0. But if you look at, for example, V2, V3, this dot product is not 0, right? 2 times 1 is 2, not 0. So right now, they're not orthogonal. And clearly, the magnitude isn't 1. Look at the middle one. The magnitude of this vector is 2. So not only they're not orthogonal, they're not magnitude 1. They're not normalized. So let's go through Gram-Schmidt normalization process. Let me change this to my to my note. Okay, so I've written the information and we want to create orthonormal sets. So first, remember in the process, we need to orthogonalize this. Orthogonalize means create orthogonal set. How? Well, W1 equals V1. Okay, so that's always the first one. So that would be for number 34. It's going to be 0, 1, 2, right? That's V1, V2, V3. W2 is, this is from Gram-Schmidt, by the way. We're doing Gram-Schmidt. V2, W2 is V2 minus the projection of V2 onto W1. Okay, that's W1, inner product W1, W1. Okay, that's V2. So that means V2 is 200, 200 minus the dot product. Remember, this is inner product, V2 dot W1. The dot product of this vector, 200, dotted with W1, which is 0, 1, 2, right? That dot product is going to be 0, isn't it? That's going to be 0. Again, W1 is this one, V2 is this one. When you do dot product, 0 by 2, 0, 1 by 0, 0, 2 by 0, 0. So that's 0 over the magnitude of W1, W1. That's when you dot it by itself. That would be square root of 5, wouldn't it? 0 squared, 1 squared, 2 squared. That's 5. And there you have it. Oh, it's the magnitude squared, right? So I don't have square root. But that's going to be 0 anyways, isn't it? True. So that's going to be 0 anyway. And let's, yeah. And then times W1. And then what is W1? W1 is 0, 1, 2, right? That's W1. So this is going to be 0. So 200 minus 000, in other words. So what does this become? W2 becomes just 200. Okay. Now, let's see. So W1 became, yeah, that would remain square root, by the way. It's not squared. All right, let's do W3. W3. And because the basis vector, by the way, has 3 vectors, W, which would be B prime, the orthogonal version, is going to have 3 vectors. What is W3? W3 is V3 minus the other 2. It's going to be minus V3 and dotted or inner product of V3 and W1 over the inner product of W1 with itself times W1. That puts it in the direction of W1 minus V3. You project it to, again, this fraction is projection of V3 onto V1, then V3 onto V3 onto W2. First one, projection of V3 onto W1. This one, projection of V3 onto W2, divided by dot product, inner product of W2 with itself in the direction of W2. There you have it. So V3, the third vector, it's going to be 1, 1, 1 minus V3 dotted with W1 means this vector. Now dotted with this vector. So 1 by 0 is 0. 1 by 1 is 1. 1 by 2 is 2. Right? So the numerator is 3. Again, that's 1 plus 2. That's 3. The denominator is W1 dotted with itself. This dotted with itself, you square each of those, take the square root, get 1, 4, adds to 5, take the square root, becomes 3/5. Right? And Let me see real quick. Oh, the dot product gives you the magnitude squared, so you actually don't have square root, right? Correct me if I'm wrong, but yeah, the dot product gives you magnitude squared by itself, so it's just 3/5. Okay, times W1, which is 0, 1, 2. So that means up here also, this should be 5, not square root of 5. Again, dot product of a vector with itself. It gives you the magnitude squared. So that's just going to be 5. The answer won't change because 0 over 5 is 0. Okay, so we got this part right. Now let's do the next one. The next one is dot product of V3 with W2 with this one, with this vector. So it's 1 by 2, and then the others are 0. Okay, so the numerator is just going to be 2, correct? Let's see, what is the denominator going to be? The dot product of W2, this vector by itself. You get 2 squared, 0 squared, 0 squared. Sum of those is 4. Dot product gives you the magnitude squared, no radical. So that's 2/4. And that's it. We multiply this by W2. W2 is 2, 0, 0. And what do we get here? 1. 3/5 times 0 is 0. 2 times 2, 4/4 is 1. So it's 1 minus 1. We get 0. The second component, it's 1. Negative 3/5 times 1 is negative 3/5. So it's 1 plus negative 3/5. That's 2/5. 2/4 is 1/2 times 0 is 0. So the second component, therefore, is 2/5, right? 1 minus 3/5. The last component is 1. 2 times 3 is 6/5, negative. 1 minus 6/5 is negative 1/5. And then that's a 0. So it's going to be negative 1/5. And that is W3. And you can see if we had W4, if the basis was in R4, R5, this can get really hectic, right? Okay, so now we have W1, W2, W3, right? So this would be our B prime, if you will. Our B prime, these are the orthogonal vectors now. They are mutually orthogonal. It's going to be 0, 1, 2. The second vector is going to be 2, 0, 0. And the third one is going to be 0, 2/5, and negative 1/5. Right? These are orthogonal. So if we do the dot product, now you can see that's 0, 0, 0. So all the dot products are 0. So hopefully everybody's okay so far. Therefore, right now, they are orthogonalized. Okay, so the vectors are orthogonalized. What we haven't done yet is normalize them. Now, the next step, we're going to normalize them. So let's normalize. Oh, before I move on, any questions about this process so far? Okay, if you're good, now let's see how we're going to normalize this one. This is again 5.3, number 34, and we're going to now normalize. Now to normalize, that means we're going to turn each of those vectors in B prime into unit vectors, right? So the first unit vector is going to be vector in B prime. The first vector divided by its magnitude. And that'll give you a unit vector, right, in the direction of W1. So it's going to be 1 over, and this is now magnitude of W1. Remember, W1 was 5. Magnitude of it is going to be square root of 5. Because W1 dotted with W1 gave you 5. The magnitude of W1 would be square root of 5 now. Multiplied by W1, which is 0, 1, 2. And this will give us our first orthonormalization orthonormal basis. 0, 1 over root 5, 2 over root 5. This vector has a magnitude 1. Okay. U2, the second orthonormal basis vector is the vector over the magnitude of the vector. Good. So that's going to be 1 over the magnitude of this. Remember, W2 inner product, dot product by itself was 4. Take the square root of 4 times 2, 0, 0, puts it in the direction of that. So you get 1, 0, 0. The magnitude of this vector is 1. And finally, U3 is W3 over the magnitude of W3, right? And the magnitude of W3, again, W3, when we dotted it with itself, W3, we get 5. So it's going to be, right, W3. Let me write this for you. This was W3, folks. W3 was 0, 2/5, negative 1/5. That was W3. The magnitude of W3 would be square root of 0 squared, 4/25, 1/25. So it's 5/25, right? 5/25. You can break it into root 5 over square root of 25 is 5. So this is going to be 1 over root 5, isn't it? Because 5 is root 5 times root 5. So it's going to be 1 over root 5, but it's in the denominator. So it's going to be 1 over root 5 times W3, which is this, times 0, 2/5, negative 1/5. Now we're dividing 1 over root 5. You invert and multiply, and therefore we're going to get root 5 times the vector. So that's going to be 2 root 5 over 5, and invert, we get negative root 5 over 5. And there you have that one. Feel free to divide out the root 5s if you choose to, and we get 2 over root 5 and negative 1 over root 5. It's okay that it's not rationalized. So magnitude of this vector is going to be 1. Now remember, before we had B prime. So this one, the final answer, B double prime. This is now the orthonormal sets. So we go U1, 0, 1 over root 5, 2 over root 5. The first vector, right? This one. This is U1. The second one we found, U2, was 1, 0, 0. This is the second normalized vector in the basis, the orthogonal basis, that is, and W3 was this one, right, which normalized into that. So it's going to be 0, 2 over root 5, and negative 1 over root 5. And this is our U3. You see how that went, folks? So, and this is the final answer. The set is orthonormal. That means the dot products of these 0, magnitude of each vector is 1. It's kind of like your IJK kind of process now. So here's how, again, the process went. We went from set B that was made up of vector V1, V2, V3. Then we went to set B prime. In B prime, we created W1, W2, W3, right? These were orthogonal. True. And finally, the one we just wrapped up, this one, these are the orthonormal sets, which, because they're unit vectors, each has a length 1. We use U for those. And so this is kind of the progression on how this process works. And these are now orthonormal. The U's are normalized. W's are orthogonalized. Put together, we get the orthonormal. And there you go. That's all there is in this one. So hopefully everybody's able to follow this work. Are we good on this work? I mean, we could spend a lot more time on this, but unfortunately our time's limited. So we won't be able to do that. Okay, is everybody okay on what we have done here? We're good, everyone?
Yeah.
All right, fantastic. So we're done with this section. This is really all we wanted to do in this section. And that means we're done with chapter 5. Now, if everyone's good on this, let's go ahead and go to chapter 7. We will probably be able to do, I'm sure, not probably, but I'm sure we're only going to be able, because it's 8:30. I can't believe, folks, how time flies in this. Unbelievable. 3 hours goes like it's 30 minutes. But it's all good, and that's fine. So let's go to chapter 7 now. The extent of what we've done is you can pretty much expect what we've done. This is what you see here. Okay, I'm skipping 5.4, 5.5. These I do separate lectures for. Really cool sections, by the way, the applications. Let's go to chapter 7. Let me see. There you go. There's a faster way to get there. Our last chapter. So in chapter 7, we're going to talk about eigenvalues and eigenvectors here. Okay. So section 7.1 actually is eigenvalues and eigenvectors. So let's go to that section. There you have. Now, the problem, the eigenvalue problem, it's actually pretty simple, okay? So the problem is this, folks. Suppose here we have, right down here, we have a system, AX. Remember, A is the matrix of coefficients. So this matrix A is a square matrix, order n, okay? And given this A, we want to know if we can find we want to know whether the non-zero vectors in X in here, AX, remember X is a vector of unknowns, X1, X2, X3, like that. So the non-zero vectors of X in Rn, do these exist? So that we can write that system, exact same system, in the form of a scalar multiple. The lambda here, this is Greek lambda, very common letter Greek alphabet to use for eigenvalues. Okay, so can we write it as the scalar? Eigenvalue is a scalar, it's a constant, as a constant times the matrix. Okay, so again, the quantity on the left, here you have a matrix, right? Square matrix times X. That's going to give you a matrix. And to the right, we have a scalar multiple of matrix X. Because they're equal, so this lambda X is going to be, again, think of it as in terms of a vector. It's going to be a scalar times a vector. So it's going to give you a vector that's parallel to X. Lambda X would be parallel to X. Now, the scalar lambda, as you can see, is called the eigenvalue. And then lambda, by the way, is going to be real numbers, or it could be complex numbers. But in this course, in this chapter, we only look at real numbers. So all our eigenvalues would be real. Okay. Now, the non-zero vector X, this vector is called the eigenvector. Eigenvector corresponding the eigenvector of n, the square matrix A, corresponding to lambda. Okay. And again, lambda x is going to be a vector parallel to vector x. And here you have the graph. See, they see the parallel going in the same direction as x, or they are parallel except going in the opposite direction. That's when lambda is negative. So that's all the eigenvalue and eigenvectors are. Let's take a look at the definition of those now. So suppose we have again a square matrix. This is a matrix of coefficients in the system of equations. So let's say that's you have square matrix, and then you have this scalar lambda, which is the eigenvalue of matrix A. See that? It's eigenvalue of matrix A. So it is called eigenvalue if there is a non-zero vector x so that this equality holds. So our task is to find lambda here, folks. Okay, that's scalar. And once we do, we can write the eigenvectors. Vector x, this vector x, which is a scalar multiple of x, is called eigenvector of A corresponding to lambda. So that's pretty much, that's all we want to do. So let's see. So let's take a look at, well, there is an example here, but let's take a look at, I'll make an example up so we can look at it. A simple example at that. So here's our example here. This is in chapter 7, section 7.1. Let's just call it an example. Okay, so in this example, suppose that my vector x is simple vector x1, x2. So I have two components, right? Suppose this is an eigenvector. Suppose this is an eigenvector of a matrix A of coefficients, square matrix order 2. So it's got to be a 2 by 2. Let's say it's 3, 0, 8, negative 1, something like that. Okay, so this is the eigenvector of that matrix. And suppose that corresponds to, corresponding to the eigenvalue lambda equal 3. So again, x is the eigenvector of matrix A corresponding to lambda. What we want to do is find lambdas in here. I've given you everything, but what we want to do in a few minutes, we want to find lambda, and from lambda, we want to find x. That's all. So we can write ax in the form of lambda x. This is all we want to do here, folks. Solving differential equations, you do that in the differential equation class. So let's do this. Then ax here, what does ax look like? Ax is going to be 3, 0, 8, negative 1. And this is an eigenvector, right? So times 1, 2. And multiply matrix, you go 3 times 1, 0 by 2. So the first component is 3. Second row, first column, give you second, first in the product matrix. 8 by 1 minus 2 is going to be 6. And if I factor the 3 out of this, I'm going to get 3 times 1, 2. You see that 1, 2 here? So that's going to be 3x. And therefore, if you notice here, ax is equal to 3x. And this is our lambda, the eigenvalue. So geometrically, eigenvalues, these eigenvalues like lambdas, what they do is they scale x. Let me write that for you. Eigenvalues, that's all they do. Eigenvalues scale. When we say scale, means a constant multiple. They scale it, like make it twice. In this case, make it 3 times the size. There you go. That's what eigenvalues do. So let's say my matrix X is 1, 2. Here's 1. Here's 2. There you go. That's that one. Now it's 3 times the size, right? It's 3, 6. 1, 2, 3. I suppose 6 is up here now. Has to be in that direction. Let's say there you go. This is going to be 3 times x if that's x. So that's what that does. It scales it and it keeps it in the same direction. Okay. Now, let me change my share and we're going to go to the book. Okay, so that's what that is. Now, let's talk about eigenspace here. Okay. Now, associated with every eigenvalue, there are actually infinite eigenvectors. We can find infinite eigenvectors, right? Because remember, eigenvalues is scale x. So you can have a vector that's twice the size, 20 times the size, half the size. They're all scalar multiple of x. So for every eigenvalue, there are infinite eigenvectors, right? Because every scalar multiple of x is also an eigenvector. So that suggests, therefore, because now we have infinitely many eigenvectors for a given eigenvalue, so sounds like we have an eigenspace, right? Remember, like a vector space is a space made up of a whole bunch of vectors. Now we have eigenspace. An eigenspace, therefore, is a vector space made up of eigenvectors. Okay. Now, let's see if we actually have. Oh, let me read this theorem, and then I'll show you that this corresponds to an eigenspace corresponds to a vector space. So theorem 7.1. Suppose A is a square matrix with eigenvalue lambda, the set of all eigenvectors. Remember, there's infinite. The set of all eigenvectors of lambda together with a zero vector. This is a subspace of Rn. The subspace, they call them eigenspace. There you go. Okay. Now, let me go back to my notepad here. And let me share something with you now. Okay. So pretty much if we have an eigenspace, then that means A times Cx can be written as C times AX. Remember, C is a scalar, so you can bring it outside, right? CAX. And up here, we said suppose we have the eigenvectors corresponding to A. So this is assumed to be true. So instead of AX, I'm going to write lambda x. So this is going to be lambda x, right? And again, the example is up here for it, the numerical example. So this is true. Well, this means that the operation is going to be closed under scalar multiplication, right? Why? Because C and lambda are scalars. I can bring lambda out, write it as Cx. You can swap them, right? Commutative property. So we just showed that ACX is equal to lambda Cx. In other words, we showed that this operation is closed under scalar multiplication. True? That's what we just showed. Now, what about closure under vector addition? Well, let's take a look at that one. Suppose now I have two eigenvectors. There are infinitely many. I'm just looking at two of them. Okay. This we can use distributive property, write it as ax1 plus ax2. Okay. Now ax1 is lambda x, right? So that would be lambda x1 plus, we replace ax2 with lambda x2. And then we can factor lambda out. So we get x1 plus x2. True. So therefore, we just showed that this is again in the form of a matrix, square matrix times sum of two vectors is a vector, right? Equal to lambda scalar times sum of the same two vectors. So we just showed that this operation is closed under vector addition. And remember the requirement to be a subspace, we needed one more. We had two things. We have to have closure under vector addition, and we have to have closure under scalar multiplication. The other requirement was this, the set has to be non-empty, right? So let me write that one. So here we have the set of all eigenvectors. Okay, the set of all eigenvectors of, let's say, given lambda of a given eigenvalue with, let's say, with zero vector. The zero vector zero forms a subspace. So we just showed again requirement for subspace. The set has to be non-empty. There you go. That makes it has zero, so it's non-empty. Close under addition and scalar multiplication. Therefore, it's a subspace of Rn. And this one, it's called an eigenspace. Called eigenspace. There. Because it's made up of eigenvalues and eigenvectors. So it's called an eigenspace. Okay. Everybody okay with this idea, I hope. Boy, we're getting close to the finish line, folks. Oh my, that's fine. Let's take a look at, I'll keep you another 5 minutes if you guys are okay with that, and then we'll let you go. Now, we talked about theorem 1 already, right? Okay. Let's see. Let's look at theorem. The question might be, well, how do I find the eigenvalues, right? And eigenvectors. I'll show you that next time, but let's go through this theorem and then we call it the evening. For this theorem, the theorem, actually it's right up here. But again, we do this, what's up here? We'll do this next week. So the theorem 2, suppose we have a square matrix. The eigenvalue of A is a scalar lambda. And there you go. This is how you find it, such that the determinant of this matrix is 0. That's how we're going to find the eigenvalues. How do we find the eigenvectors? The eigenvectors of A corresponding to an eigenvalue are non-zero solutions of this matrix. And there you go. And that's what we're going to do next week, folks. We're gonna talk about this and look at examples. Now, what's going to happen, and we're going to use, most likely we can use Symbol Lab next week because we're talking about finding solutions to a homogeneous system here in number 2. So we're going to use Symbol Lab to make our work easier. Now, this equation, determinant of lambda I minus A equals 0, they call that the characteristic equation of A. Okay. And the resulting, once you do lambda I minus A, again, this may not make sense to you right now. It's like, what the heck is this? But once we put numbers to these, you'll see what's going to happen as a result of this determinant. We're going to get a polynomial function in lambda. See, lambda to the n minus 1. This is a polynomial function. So they call this the characteristic polynomial of A. That's what this polynomial is. So you have characteristic equation, the characteristic equation. The determinant is called characteristic polynomial. Okay. Now this polynomial has precisely n roots if we count complex roots. This goes back to pre-calculus days. I know it's been a while. Remember, a polynomial with real coefficients has precisely n roots if we count repeated real roots as well as complex roots. So this characteristic polynomial will have exactly, precisely n roots. Okay. And we will find these next week. Okay. So let me stop again. It's 8:51 here. I don't want to worry you down too much because the next examples will take more than 5 minutes, and I don't want to keep you too long. I appreciate your patience being here this late. So that's good enough for me. So let me actually stop here. And so I'm going to stop the recording. There you go. And